I want you to imagine, just for a moment, uh, trying to farm at the very top of the world.
Right, which is no small feat.
No, not at all.
Yeah.
You are standing in a high-altitude cold desert. During the short summer, the sun beats down on you, and the temperature swings up to, like, a blistering 33 degrees Celsius.
Yeah.
But then in the winter,
Oh, it plunges.
yeah, to a bone-chilling minus 28 degrees.
It is, it's just an incredibly hostile environment for anything biological, let alone trying to grow a delicate agricultural crop.
Hmm.
We're talking about a region where survival is balanced on a nice edge,
Right.
largely because, rainfall is practically non-existent.
Which brings us to today's topic. Welcome to this custom deep dive. Today we are exploring a fascinating recent study out of the Trans-Himalayan region of Leh, Ladakh in India.
It's a really incredible paper.
It totally is. The title is Hydrochemical and Quality Assessment of Irrigation Water at the Trans-Himalayan High-Altitude Regions of Leh, Ladakh, India. And our mission today is to uncover a hidden reality about survival in one of the world's most extreme environments.
Yeah, because we are going to look at why the specific chemical makeup of water, not just the volume of it, but the actual chemistry, is the ultimate secret to keeping agriculture alive in a place like this.
Because I think we usually just think, oh, plants need water. Give them water, they grow.
Right, but in fragile mountain ecosystems, water isn't merely like a physical resource that keeps plants hydrated. The chemistry of that irrigation water dictates absolutely everything.
No,
Literally everything, from the physical structure of the soil to the region's overall food security over the long term.
So I think to really grasp the stakes here, we have to understand the actual landscape this water is flowing through. Because before we read this, I didn't realize quite how extreme it was.
It's basically a completely different world. We're talking about Leh, Ladakh. It's a high-altitude trans-Himalayan region. And the soil there, it's over 80% sand.
Wait, 80% sand? That sounds less like traditional agriculture and more like trying to terraform a harsh, sandy planet.
That's a really good way to put it, actually. And it presents an immediate physical problem. Sandy soil has high microporosity.
Meaning the gaps between the particles are big.
Exactly. So it doesn't hold on to moisture or nutrients very well. Water just drains right through it.
And to make matters more complicated, the sky offers zero help, right? Like I read that in 2015, they recorded virtually zero rainfall for the entire year.
Just 0.0 to 8 millimeters, basically nothing.
So agriculture relies entirely on these narrow, traditional canal systems. I think they call them nalas.
Yeah, nalas.
Yeah.
And these canals carry glacier meltwater, snowmelt, and river water from sources like the Indus River, bringing it directly to the fields.
But this total reliance on meltwater, it shifts the entire agricultural paradigm, doesn't it?
It really does. I
Yeah.
mean, if you are farming in a place with abundant rainfall and deep, loamy soil, you have a natural buffer.
Because the rain sort of dilutes things.
Exactly. Rain is relatively pure, and rich soil can absorb a lot of chemical punishment. But in Leh, the soil is incredibly fragile. Because they are completely dependent on these specific meltwater canals, the chemical quality of that irrigation water becomes the single most important determinant of success.
Because if the water introduces, say, harmful chemicals or excess salts, there's no fresh rain coming to flush the system clean.
Right. The soil just accumulates all that damage. The margin for error is essentially zero.
Wow.
Yeah, if the irrigation water degrades that extremely limited cultivable soil, the plants fail, the soil structure breaks down, and the entire local food system collapses.
Okay, so given that total, absolute reliance, we have to look at what is actually hitting these fields, because as this paper points out, it's not just pure H2O.
No, definitely not.
To figure this out, the researchers took 70 different irrigation water samples from 7 representative villages across the region, places like Rambipur, Thiksay, Chocho, She, and they were looking at the physicochemical basics, right?
Yeah, so things like pH, electrical conductivity, total dissolved solids, and a whole host of specific minerals and ions.
Here's where it gets really interesting to me, because I think most of us assume, or I definitely assumed, that high-altitude glacier meltwater is like the purest, most pristine water on Earth.
Oh, for sure. If you are picturing a crystal clear, untouched mountain spring right now, you're not alone.
Right. But the reality is that this water is packed with dissolved minerals and salts. Why is that?
Well, we see a glacier and we just think of a giant ice cube. But you have to think of water dynamically as a universal solvent.
Meaning it dissolves whatever it touches.
Exactly. As this water melts and flows down the immense vertical drop of the Himalayas, it is constantly grinding against millennia-old rock. And as it does, it's picking up dissolved minerals like calcium, magnesium, sodium, and silica.
So it's essentially acting like a cargo train moving down the mountain. The glacier meltwater starts as an empty train, but as it rolls past different geological stations, it picks up different elemental freight.
That cargo train analogy captures the mechanism perfectly. And this delivery system is what brings essential nutrients to the plants.
So it's not inherently a bad thing.
Not at all. For instance, the researchers found that the water in these villages is naturally alkaline, with the pH ranging from roughly 8 to 8.6.
But wait, when people hear alkaline or high pH, they might think, chemical pollution.
Right, but this alkalinity isn't from human pollution or industrial runoff. It's due entirely to the natural weathering of the rocks it passes over.
Got it. And they also measured electrical conductivity and total dissolved solids, which both came back in the moderate or quote-unquote good category.
Which is huge, since electrical conductivity tracks the concentration of dissolved ions, basically telling us how salty the water is. This seems like a massive hurdle cleared for the farmers.
Because high salt would just prevent the seeds from sprouting entirely.
Exactly. It is a critical baseline to pass. But the researchers didn't just want to know how much cargo the water was carrying.
They wanted to know where it came from.
Yes, they wanted to trace exactly where it came from and how it behaved. This is the concept of hydrochemical evolution.
Hydrochemical evolution. Let's unpack that.
So, water inherently wants to reach a state of chemical equilibrium with its surroundings. The ions we see in the water originate naturally through the continuous weathering of silicate and carbonate rocks.
So as the water flows, it dissolves minerals, and it's constantly evolving its chemical signature based on whatever rocks it's currently touching.
Exactly. And to map that evolution, the scientists used a few specific visual tools. They used Piper diagrams, Durov diagrams, and the USSL diagram.
Okay, I want to pause on these because they sound like intense academic jargon.
They do sound intimidating.
But looking at the paper, they're actually just really clever ways of plotting data to reveal different behaviors. I was thinking of it like this: these diagrams, they act like a genetic ancestry test for the water.
Oh, I like that.
Yeah, they tell scientists exactly which rocks the water hung out with on its way down the mountain.
They really are essential tools in hydrochemistry. A Piper diagram, for example, plots the relative concentrations of different positively charged callaches and negatively charged anions.
Okay, positively and negatively charged ions.
Right. It uses two triangles that project data into a central diamond. And by looking at where the water samples cluster in that diamond, scientists can instantly classify the water type.
And what did they find for ley?
In this study, the Piper plot revealed the water was mostly a calcium chloride sulfate type, or a sodium-potassium bicarbonate type.
So the Piper diagram gives us a snapshot of the cargo currently on the train. It tells us the water is carrying calcium and sulfates, which means the train definitely passed through stations made of gypsum, carbonate rocks, and silicate rocks.
It gives you the composition, yeah. But then we move to the Durov diagram, which takes that same cation and anion data and plots it on a slightly different grid, adding in pH and total dissolved solids.
What does that add to the picture?
Well, the Durov diagram doesn't just show composition. It reveals the hydrogeochemical processes at play. It shows whether the water is mixing with other sources, dissolving new rock, or actively exchanging ions with the soil.
Ah, and that ion exchange is the really crucial part here, isn't it?
It's massive. The researchers calculated these things called chloralkaline indices, or CAI, and they found positive CAI values across the board.
Okay, positive CAI, what does that actually mean for the water?
When we see a positive CAI, it indicates a direct base ion exchange in the groundwater system.
Meaning the train isn't just picking up cargo, it's actively trading freight with the rocks and soil as it moves.
Exactly. The water trades away its sodium and potassium, and in return it takes calcium and magnesium from the host rocks.
That's incredible.
It is. This natural weathering and trading process is what determines the final mineral balance of the water before it ever touches a crop. And the study noted there were only very minor inputs from human activities, mostly isolated to the villages closer to the main city of Leh.
Okay, so we have this water that has inherited its chemical makeup from the mountain itself, trading minerals back and forth. But, a farmer doesn't necessarily care about the paper diagram.
No, they care about their crops.
Right. They just want to know if it's safe to use. So scientists grade this water using a series of irrigation water quality indices. It's basically an incredibly detailed report card.
And it looks at a lot of factors: the sodium hazard, the permeability index, Kelly's ratio, total hardness, and the magnesium hazard.
Let's start with the big one. What is the most critical pass-fail metric on that report card,
Oh, definitely the sodium hazard.
which thankfully came back low for this region?
Yeah, the USSL diagram, which specifically plots salinity hazard against sodium hazard to give a direct practical recommendation for agriculture, it confirmed a low sodium risk.
And they also evaluated this using the sodium adsorption ratio, or SAR, and Kelly's ratio, right?
Correct. Both SAR and Kelly's ratio are mathematically comparing the amount of sodium in the water to the amounts of calcium and magnesium.
It's like a battle for dominance.
Exactly, and you want those ratios to be low because excess sodium is an absolute soil killer, especially in an environment like this.
Walk us through the actual mechanism of that, because I think it's fascinating. If the sodium train arrives at the farm and unloads too much sodium into the soil, what actually happens to the ground?
Okay, so if irrigation water is dominated by sodium, those sodium ions force their way into the tiny clay particles in the soil, physically pushing out the calcium and magnesium. This process is called deflocculation.
Deflocculation.
Yeah.
So the soil particles actually repel each other instead of clumping together.
They completely disperse. The soil loses its internal structure and porosity. It becomes totally impermeable to water and just dries into a hard, concrete-like crust.
Wow, like concrete.
Literally, plant roots physically cannot push through it. They can't access oxygen, and any subsequent irrigation water just pools on the surface and evaporates.
So if there was a high sodium hazard, farming would just be impossible here.
Pretty much. The fact that this Himalayan meltwater naturally trades away its sodium on the way down the mountain, keeping the sodium hazard low, is the primary reason agriculture is even possible in Leh.
It's like a natural fail-safe built into the mountain's geology.
It really is.
But looking at the rest of the report card, we see the trade-offs of that low sodium. Because when the water traded away its sodium, it picked up something else.
Calcium and magnesium.
Right. And the researchers found elevated levels of total hardness and a high magnesium hazard. Most of the water fell into the moderately hard to hard category.
Yeah. And hard water is defined primarily by those high concentrations of dissolved calcium and magnesium.
Yeah, I know hard water is annoying in a shower, but what does it do to a farm?
Well, while it won't turn the soil to concrete like sodium does, it presents a much sneakier problem for the farmer: nutrient lockout.
I really want to focus on this because it highlights how complex plant biology actually is. You can have soil packed with all the nutrients a plant needs, but if the water chemistry is wrong, the plant basically starves while sitting at a buffet.
That is the perfect analogy. Plants require a very specific, diverse diet of micronutrients, and they absorb these nutrients through a process of cation exchange at the root level.
Okay.
But when the irrigation water constantly floods the root zone with heavy dominant ions like calcium and magnesium, those ions overwhelm the plant's receptors. They literally crowd out other vital nutrients.
So the calcium just takes up all the parking spots on the plant's roots?
That is exactly the mechanism at play. Specifically, high calcium and magnesium can severely inhibit a plant's ability to absorb iron, potassium, and phosphorus.
Which connects directly to previous agricultural studies from the Leh region, doesn't it? I read that local crops often suffer from iron deficiency.
Yes. And the irony is, the iron is physically present in the sandy soil.
But the hard water locks the plant out of absorbing it.
Exactly. It requires meticulous long-term soil management from the farmers. They have to monitor their fields constantly, sometimes adding specific organic matter or amendments, just to ensure the plants don't starve for micronutrients while they're drowning in calcium.
So the water is suitable for irrigation, but it demands active, constant management.
Very active.
It's a relentless balancing act. You fix the physical soil problem by avoiding sodium, but you create a biological nutrient problem with the calcium.
And that balancing act extends beyond just the biology of the plants. It actually affects the physical infrastructure of the farms themselves. Which brings us to one of the most practical, fascinating findings of the entire study.
The corrosivity ratio.
Yes.
I found this part of the research completely arresting because it highlights the unintended consequences of natural chemistry.
It really catches you off guard.
Right. So the study calculated the corrosivity ratio across all the locations.
Yeah.
And they found that everywhere they tested, the value was greater than 1. In the village of Nemo, it even approached a 5.
And just for context, in the world of hydrology and water management, a corrosivity ratio greater than 1 is a massive red flag for any infrastructure.
It's wild to think about. Think about the pipes in your own house, right? We just assume if water is safe to drink and safe to pour on our vegetables, it must be completely benign.
It seems logical.
But this water, which is perfectly safe to grow the food these communities eat, will literally eat straight through a solid metal pipe.
It will. And it all comes back to the specific cargo the water picked up on its journey.
The sulfates and chlorides.
Exactly. The combination of chlorides and sulfates in the water, working in tandem with the natural alkalinity, creates a highly corrosive electrochemical environment.
Now, the chemistry of corrosion is essentially electron theft, right?
It is, yeah. The aggressive ions in the water, particularly the chlorides, facilitate an electrochemical reaction that steals electrons from the metal irrigation pipes.
Leaving the metal structurally compromised.
Right, it causes rapid oxidation, rusting, and ultimate structural failure of the metal.
What makes this finding so brilliant to me is how it validates the lived, on-the-ground reality of the locals.
Oh, absolutely.
For years, farmers in these high-altitude villages have dealt with their metal irrigation channels degrading, rusting out, and failing far earlier than any manufacturer warranty would suggest. You can imagine the frustration of buying expensive metal piping, hauling it all the way up into the Himalayas, and just watching it crumble in a few seasons.
They likely assumed the materials were just defective, or maybe that the extreme temperature swings were cracking the metal.
But the culprit was invisible. It was the water itself, actively dismantling the metal at a molecular level.
And the scientific recommendation derived from this is incredibly straightforward. Abandon metal infrastructure entirely.
Just stop using it.
Yeah, the researchers explicitly advised the local agricultural community to transition to PVC, high-density plastics, or specially coated, rust-resistant materials for all their irrigation networks.
It is such a striking example of how highly complex geochemical science, like tracking the weathering of silicate rocks on a mountain peak, translates into a direct money-saving practice for a farmer just trying to water their field.
It takes the invisible mechanics of the world and makes them visible and, more importantly, actionable.
So we've followed this incredible journey of water in Leh Ladakh. It starts as glacier and snowmelt, high up in an unforgiving, rainless desert.
It flows down the mountains, chemically evolving as it grinds against silicate and carbonate rocks, trading its sodium for calcium.
Right, and then it arrives at the fields as this complex, alkaline, nutrient-carrying lifeline. It has a low sodium hazard, preserving the fragile structure of the sandy soil.
But, as we've seen, it is hard enough to cause a nutrient lockout for the crops and electrochemically aggressive enough to destroy the farmer's metal infrastructure.
It is the ultimate chemical cocktail that makes life possible at the top of the world.
It really is a marvel.
But looking at this research, especially considering the fragile equilibrium we just mapped out there, is a looming implication for the future that we have to address.
Yeah, and it's a big one. The entire hydrochemical balance of this region, the very ability of these communities to grow food, relies on a highly specific cycle of rock weathering and glacier melt.
It's a system in delicate equilibrium.
Exactly. But we know that the global climate pattern is fundamentally altering.
The glaciers in the Himalayas are retreating at unprecedented rates.
And as the volume, the temperature, and the speed of that meltwater change, the dynamics of this water-rock interaction are guaranteed to shift.
Because it alters how the water flows over the rock.
Right. Water might spend less time in contact with certain rocks, or entirely different geological layers might be exposed as the ice recedes.
To use our analogy, the route of our cargo train is going to change, which means the freight it picks up is going to change.
Exactly. And I want you to consider the magnitude of that shift. If the changing climate alters the fundamental chemistry of the mountains, how will the agriculture of the future adapt to a completely new chemical baseline in their water?
That's a really intense question.
Right. If the weathering process changes and the sodium hazard increases, or the alkalinity spikes beyond manageable levels, the farming techniques that sustain Leh today might fail entirely tomorrow. It's not just a matter of having enough water as the glaciers shrink. It's about what that water is going to be made of.
It is a totally sobering realization. I feel like we spend so much time worrying about the rising temperature of the landscape, but we rarely consider that the fundamental chemistry of the landscape is changing right beneath our feet. The water of tomorrow might not be the water of today.
It's definitely something to think about.
Well, thank you for joining us on this deep dive. The world around us is packed with these invisible, intricate systems, turning something as ubiquitous as a drop of water into a complex mechanism of survival. Keep exploring the hidden science in your everyday world, and we'll be right here waiting to unpack the next big idea with you.